Hey there, welcome to my YouTube channel. This is Unit 1 Electrostatics and we are discussing applications of Gauss Theorem. The third application which we are going to discuss today is electric field intensity due to uniformly charged solid sphere. But the thing is, before applying the Gauss theorem, we need to consider a solid sphere which we already have. That is a solid sphere which is shown in pink color with having a radius of capital R and is charged uniformly such that a Q charge is spread all around its surface. And as we already know, in order to apply the Gauss theorem, we always need a Gaussian surface which could be of any shape or of any size, but it should be a closed surface. We always consider a Gaussian surface which is geometrically symmetrical, and hence the most suitable Gaussian surface in order to find electric field intensity due to uniformly charged solid sphere is the sphere only. So I have chosen a Gaussian surface to be a sphere of radius small r, and now we need to find the value of electric field intensity. And in order to find the electric field intensity, we as usual have to apply the Gauss theorem. And according to the Gauss theorem, we have closed integral E vector dot ds vector is equal to q upon epsilon naught. Now, let us consider an electric field line. I will consider only a single electric field line leaving the surface as the sphere is charged positively. Therefore, electric field line will leave the surface normally and it will act in the outward direction. As in previous case, we have already discussed that these electric field lines are leaving the surface in all the directions like this. But we are not drawing each and every line of the electric field line because it will make our diagram a bit of messier one. So it is better to only draw the single line, and we always know that this electric field line leave the surface normally. So here the angle is 90°. Now I need to divide my Gaussian sphere into small number of surfaces, infinite number of surfaces which are equal. So let us consider a small portion ds of the Gaussian surface. And this Gaussian surface is divided into infinite number of small portions. And now we need to consider a area vector, and in order to find the area vector, the considered surface is ds surface, and we will draw a vector pointing away from the considered area and leaving the area normally. So in this direction we will get ds vector. So this area vector is also leaving the considered area at an angle of 90°. Therefore angle between E vector and ds vector is 0°. Now, from this equation which we have written from the Gauss law, we can rewrite it as closed integral E ds cos 0 is equal to q upon epsilon naught, and we know cos 0 is 1. So 1 multiplied by E into ds is E ds. Therefore, we are left with E ds is equal to q upon epsilon naught. Taking E outside the integral, we will be having E is equal to closed integral ds is equal to q upon epsilon naught. Now, integral means to add up all such infinite number of small surfaces. So when we will add up all such infinite number of small surfaces, we will be having a complete sphere, that is a Gaussian sphere of radius small r, and the surface area of sphere is given by 4 pi r square. Therefore we have E into 4 pi r square is equal to q upon epsilon naught, and rewriting this equation we will get E is equals to 1 upon 4 pi r square q upon epsilon naught. Just rearrange this equation, and we will get E is equal to 1 upon 4 pi epsilon naught q upon r square. So this equation is same as we discussed in the previous article. So what is the difference when we calculated electric field intensity due to uniformly charged hollow sphere, and now we are calculating it for the electric field intensity for uniformly charged solid sphere if the expression is going to be same. So in this case we will not find any kind of difference because the Gaussian surface is enclosing a same charge, small q charge. For Gaussian surface it is not a matter of consideration whether the charge is carried over a hollow sphere or the charge is carried over a solid sphere. We need to discuss some special cases in order to find out the difference. So let us discuss the various cases as we discussed in the previous article. So first case is if radius of Gaussian sphere is greater than the radius of the solid sphere, capital R. So nothing is going to happen. The case is same which we have already discussed, that is we will be having in that case E is equal to 1 upon 4 pi epsilon naught q upon r square, or we can say E is inversely proportional to r square. So our article is same, the expression is same in this case which was earlier in case of uniformly charged hollow sphere. Now we will consider the second case. Again in second case we will be having if radius of Gaussian sphere is equal to the radius of the spherical charged sphere, so R is equal to capital R, we will be having E is equal to 1 upon 4 pi epsilon naught q upon capital R square, or we can say E is inversely proportional to r square. Again we are having the same condition as we discussed in the previous article. So again the difference is not lying in these two special cases. That means we need to consider the third case where actually the difference will be considered. So in third case, if the radius of the Gaussian sphere is less than the radius of the sphere over which the charge is spread uniformly. So let us say we are having a Gaussian surface represented by a blue color such that this is small r, a radius of the Gaussian sphere. Now it is not a hollow sphere, that means the charge is spread all around in this surface. So even this surface over which is of radius r, that is Gaussian surface, there will be a charge which is spread uniformly, but this charge will be different from the charge which is spread all over the solid sphere. So how we will consider how much charge is spread over the sphere of radius small r. So in order to find this small r, this small charge which is spread over the Gaussian surface which is considered to be of radius small r, we need to recall the definition and the definition of volume charge density. So we know from the definition of volume charge density that volume charge density rho is equal to total charge divided by total volume. So in this case we can say volume charge density rho is equals to, let's say the charge which is spread over the Gaussian sphere of radius small r is q dash, and the volume of this small sphere is 4 by 3 pi small r cube. From here we have the charge which is spread over the Gaussian sphere of radius small r which is less than the radius of the spherical solid surface, then q dash is equal to 4 by 3 pi r cube rho. And now we can substitute this value in the equation, that is E is equal to 1 upon 4 pi epsilon naught q dash upon small r square, because now the Gaussian sphere is enclosing some charge which is different from the charge which is spread all over the solid sphere. So now I have substituted q dash instead of writing q, because my Gaussian sphere is of radius small r and this small r radius is less than the total radius of the solid sphere. So this is the expression. And now we have already mentioned that q dash is equal to 4 by 3 pi r cube rho, and therefore we can write it as 1 upon 4 pi epsilon naught. Substituting the value of q dash, we have 4 by 3 pi r cube rho divided by r square. Now cancelling out 4 pi and r square, with this we are left with E is equal to 1 upon 3 epsilon naught r rho, or we can write it as E is equal to r rho upon 3 epsilon naught. So this is the final expression, and here we can say electric field intensity is directly proportional to r until r becomes equal to the capital R, that is radius of the solid sphere. So in case of this solid sphere, what we can see that electric field intensity keep on increasing until we reach the value of capital R, that is the radius of the solid sphere, and it will reach the maximum value until we reach the radius capital R, and after that it will start decreasing as inverse square law. So plotting it on a graph, we will find that if we consider the distance from the center of the sphere along x-axis represented by small r, and electric field intensity along y-axis represented, so here I will put y-axis electric field intensity. So in last case we have find that electric field intensity is directly proportional to r. So that means in case of directly proportional, we have a linear graph, so it will keep on increasing. So I will be having a graph such that it will keep on increasing until its maximum value, that is the maximum value will be reached when small r is equal to capital R, and after that it will start decreasing obeying inverse square law. So the portion will be like this. In case of inverse square law, we are always having a curve which is represented like this, and we will mention the various portions, and in order to mention I will write E is inversely proportional to r square over here, and E is directly proportional to R, or E is equal to maximum, and here E is directly proportional to small r, where small r is representing the radius of a Gaussian surface. So I hope you have understood this article as well, that how we can apply the Gauss theorem in order to find the electric field intensity due to uniformly charged solid sphere. Just have a look once again. We have started with the Gauss theorem, and with the help of Gauss theorem we are able to calculate the value of electric field intensity and at various points. I hope you have understood this article, and if yes, then do not forget to press like, subscribe and share button, and do press the bell icon in order to get latest notifications on my videos.